we started to actually talk about what we wanted to learn in pattern recognition, and we have started to talk about this data selection and feature selection and feature extraction. And we said that we have to deal with something which is called data redundancy, because there exists lots of redundant information which we don't want them. The data which are correlated, which are very depending on each other, we don't want them because they will not introduce anything new to us. Now, when it comes to the matter of selecting data, there are three important aspects that we have to consider. One is sample size. The second thing is number of features, and the third thing is classifier complexity. Now, what do we mean by sample size? When you hear the word sample size, what do we mean by sample size? Should it be big? Should it be small? Big. If it becomes bigger and bigger, it's better because we can consider more situations, so we can generalize if we have very big. But what is the drawback? It needs more processing power, maybe, we don't know, but definitely we need more time. And in the reality, we cannot have all the scenarios. Imagine you want to do face recognition and you want to do tests. We cannot have all the 7 billion people of the earth to be tested on the system before we release it. Second thing is number of features. We remember regarding the number of features, we have this peaking phenomenon. If we increase the number of features, not necessarily we get good results. You remember I showed you on the slide, which is actually the next slide, that the performance starts to drop if you are increasing the features. And lastly is classifier complexity. We can have a very good classifier which works perfect, but it is that much computational complexity-wise high that it may take, let's say, a couple of days to do the process. Like you need to do a face recognition, you might need about 1 hour to say that yes, you are the person or not. And imagine that you need to run into a safe room and you have to wait for 1 hour before they let you in and you are dead before the door gets open, right? So the trend is we have to find a very good point, optimal point between all of these ones. So within this course, we try to see how we can find this optimal point. You remember this slide? Which we said as the number of features increase, not necessarily the performance is increasing. Here we see that the performance is starting to drop. And we gave some information about the type of data that we have, how the size or the number of features are being increased. These are huge number of features, so we definitely need to have some techniques which reduce this amount of data or the dimensionality that we have. And we stopped by this slide which was talking about the data reduction. There exist several methods for reducing the data. One method is regression. What is regression? We are modeling the data that we have. Instead of I give you lots of data, I tell you that the data is 3x plus 2. So you know that if you put the value of x, you can get the value of y. So I do not need to provide you with data.
I have a question about the graph you showed, the relation between the number of features and...
This one?
Yeah.
This is a graph from Druxing, and this is a reference. So
I mean that if all the features are equal, so...
What do you mean features aren't equal? I don't know even what are the features.
Yeah.
Do you know what are the features?
No.
Questions. No. The aim of this graph is to show that if the features are being increased, it will drop. Look, this is true. What are these features? Maybe they are increasing the bad features. If we increase good features, we may get better results. And this is some philosophy that we can focus on that one. Here is an example that maybe they increase the bad features, but increasing the feature, the performance drop. Imagine if for each of the features you want to see whether it's a good feature. In other words, you have to calculate the within distance and between distance and see if they can discriminate very well. If you need to do it for each of these features, months, years may go, and you are still looking for which feature is good, which feature is bad. So really we cannot do it. So what we do, we say that we have all the features. Should we use it? Yes or no? Rather than, okay, let's try them one by one. And maybe after 1 year, when you find that in the facial images, these are good features, these are bad features, before you publish, maybe someone else can come and say that, by the way, did you know that we have also this feature? So you have to go and add something on top of it. So this is an infinity loop. So what Eric says is kind of true. We have to know what are these features. Maybe we are increasing the bad features, maybe. But increasing the features is not necessarily always good. Again, I don't know what this data represents. We know that it's used the support vector machine, and we know that it's supposed to be about drug screening. You can go to the reference, you can read it, but it's more than the classification paper. Anyway, let's get back. So one is we are determining a mathematical model, and we are using this model in order having the huge data. This is good. Another one is sufficient statistic. Now, what we mean, can you tell me that some statistical parameter that you know? What is the most famous statistical parameter that we use a lot in our daily life?
Mean.
Mean, average. What else?
Min, max.
Max, maximum, minimum. What else?
Standard deviation.
Standard deviation, similar variance. What else?
Median.
Median, mode. So there are lots of statistical parameters that we have. Sometimes we can represent our data by using these statistical terms that we have. Imagine any normal distribution or any Gaussian distribution, we can represent it by only mean and standard deviation. Do you remember? Last week, quickly, we were going over there and we said that the good thing about Gaussian distribution, normal distribution, is that we can represent it by using the statistic features. We use the word sufficient because only one or two may not be enough. If I tell you that in this class, the mean of the grade is 80, doesn't mean it's a good class or it's a bad class. We don't know. If I tell you that, okay, the mean is, let's say, 80, and the variance is 1, then we can have a better feeling that the variation is mostly around 80. Most of the people are between 79 to 81, so it's kind of a good class. But if I tell you that the variance is bigger, or the median is a very low number, then you can start to think, okay, this might not be a good class. So we have to know, based on the nature of the scenario that we have, how many of these statistical features we need. Another very useful way of reducing number of data is using histogram. What does histogram do is this. It defines lots of sets, lots of baskets, and tells that the data that we have, how they are filled in these baskets. For instance, I have a basket for the value 0 to 10, then from 11, let's say, to 20, then from 21 to 30, and so on. And I can fill it. Then at the end, when I look at these baskets, when I look at how much number I have in each of these ranges, I can conclude something. If you have taken the image processing course, you may remember we were looking at the histogram. We calculate the histogram of an image. We look at the mean of the histogram and we say, this is a dark image. This is a high contrast image. So by histogram, we don't need to look at the whole image. We are reducing the amount, the dimensionality. We are reducing the amount of data that we have, and we can get some conclusion. Of course, we don't say regression is better than the statistics. Or we don't say that statistics is better than histogram. Different situation, different model might be better. Clustering is also another way of reducing the size. We can cluster the terms which are very close to each other. Like we can say that terms which are red in one cluster, terms which are, let's say, yellow are in one cluster, or terms which are round in one cluster. So we can cluster the data according to that feature. And sampling, which we have to talk, is something which is very critical. We have big data, we can go and pick up some samples from this big data and say that these samples are representing my big data. Now, this is very tricky because if we do a bad sample, we will get a wrong result. So we have to see how we can do sampling. So if you want to do sampling, there exist several methods. One of them is simple random sampling. What does it do? Randomly, I go and pick up some numbers. What is the problem with that one? The problem with that one is we don't know what we are taking. Maybe it's random, right? Maybe I will pick up, imagine I want to see if the mathematics level of the students inside this class is high or low, okay? And I decide to randomly pick 3 people. And I just randomly pick 3. And maybe these 3 are, let's say, those people who are very, very excellent in math. And then, by talking with these 3, I can get totally a wrong conclusion that the level of mathematics of the class is very high. Or I might want to see what is the level of the programming, and I might randomly pick 3, and those 3 are those people who have never done any programming. Imagine that. Then my conclusion will be, oh, the level of the programming of the class is low. So this is the problem with that one. But this is simple because we know probability, we know lots of sampling techniques, so I can randomly go and pick up some numbers. There are two other ways of doing the sampling. One of them is that I am sampling, and if I pick one student, I will not replace the student back. I will tell the students that you stay here, that I will pick another one. So it's called sampling without replacement. Or I can do the same thing, but this time, if I pick one student, if I pick one thing, I will place it back. In other words, there is a probability that I will pick this student again. Now, each of these ones have their own advantages and have also their own disadvantages. And one of the ways which we prefer to use is something which is called a stratified sampling. A stratified sampling is this. I do not sample from the whole class uniformly. What I do, I group them first. Like students, let's say, who get very good grade, students who get medium grade, and the students who get very low grade. Okay? And based on how many members I have, let's say I have only 3 members in a very good, hardworking student, and 20 members in medium level students. Then I don't need to pick up 2 from each. I may pick up 1 from here, and in another group which I have higher population, I will pick up, let's say, 4. So based on the group, I do the grouping, and based on the number and the size that I have, I change the number of samples that I take. How do I know how much I have to take? I can do this. I will pick up 10% of the population of each of the group. So it means in one group I may have 10, in another group I may have 3. But if I look at the ratio, they are all 10% of the total number that they have. So there exists lots of methodology for doing the sampling. Usually the sampling that we do is a stratified sampling. It makes more sense to do it. But again, it depends on different scenario. We can have different way and different approaches. Now, big data, we have lots of big data. Handling of that one is difficult. There are lots of features. Some of them are not good. So we have to figure out how we can come up with something which is very handy for us and is very meaningful. And in this way of reducing the data, or reducing the dimensionality, there exist 2 main categories or 2 main approaches. One of them is feature selection, the other one is feature extraction. These 2 have a very important difference. In feature selection, I look at the basket of the features that I have and I pick some. So whatever I pick is it is meaningful. I can look at it and I can interpret it directly. like the color of the skin. I want to do the face detection and the color of the skin. If I pick the color of the skin, I know that what I'm talking about. In feature extraction, usually what we do is we don't pick up the feature as it is. We transfer the feature to some other domain, not necessarily changing it from time to frequency. Maybe we translate it by using some linear transformation or by some nonlinear transformation. We do some transformation, and then in this new domain, we will look and we will pick up the features. Now, whatever I pick up in here, I cannot interpret it. It does, if I look at it, I cannot say that, it talks about the color of the skin. It will be totally different thing. But it will be very useful if you want to do, let's say, discrimination. It will be good if you want to do some type of clustering. So, feature extraction, it creates new features. It creates new models. It transfers what we have to another terminology which help us in order to reduce the dimensionality or to reduce the number of data. We will talk about something which is called principal component analysis in details in this course, and it will be a feature extractor techniques. Now, this diagram will show you the feature selection very well. We have vector of x as an input to the feature selection, and we have the same vector of x as an output. But the difference is that the dimensionality has been reduced. Here I have d element, here I have m element, and m is less than equal to d. If m is equal to d, it means that I really don't need a feature selector because I have selected everything. Now, if d is the input high and m is the output low, how many ways can I select the combination of d over m? So it tells us how many ways I can select pairs or edibles from these sets of data. Again, this is something about a statistic. If you don't know it, that's all right. Now, feature selection, which we are talking today about it, can be divided into several categories based on different point of view. First point of view that we talk is we can have univariant method or we can have multivariant method. What is the meaning of univariant? You know, variant means varying, uni means one. So one varying or one variable method, multi-variable methods. In other words, in univariate method, we will focus only on one feature in order to select it. In multivariate, we will look at multi-features in order to select some. Also, it doesn't matter if it is univariate or multivariate, we can have other methods for selecting the features. We can have filter methods. Mostly univariant features are filter methods. They use the filter method. In next slide we will talk about the filter methods. We can have wrapper methods and we can have the embedded methods. Now, wrapper method is the way that we are using classifier, which is supposed to do the classification, to help us in order to select the features. How can we do it? How can we do it? See, here in the class only one person talks. Now, the question is this. In wrapper methods, we want to use classifier to tell us which features are good. How can a classifier tell us which feature is good? Very simple logic. I have a classifier and I have features. How can the classifier tell me that which feature is good?
You run the features through the classifier. And you look at the results.
Yeah. We use features, we look at the result, those features which give us good result if we pick them up. So the wrapper method says that. Is it simple?
No.
No, it's not simple. because we might need to go through all the features. Maybe the classifier by its own, its computational complexity was very high. So running it in order for the sake of finding which feature is good sometimes is not reasonable. Of course, we will talk also about some other classifier which is very simple and you can apply the wrapper method. But again, you know, I think in 4 or 5 slides later you will see a slide that I have put that you have to look at your application, the amount of accuracy that you want, and the amount of time and money that you can really spend for that. So if you have infinity many money, infinity many time, and you want to have a very high accuracy, it's only research, you don't talk about the practical aspects, then you really don't mind if training your classifier to choose features takes less than 1 month. We were working on something for super resolution, and the experimental result took about 3 months. And we didn't care, because for us it was important to get to some research results. And we were assuming that maybe 5 years later we have super fast computer everywhere, and that 3 months task will be happening one day. So sometimes you don't care. Sometimes you want to have an attendance system here. So we want to see who is coming to the class and who is not, and you really cannot wait for 3 months to recognize each of the single people, right? So you have to find an optimal point at which method you are selecting. And you have an embedded method. In the embedded method, you do not, okay, before we come to here, usually what happens, we are selecting the features. Before I build the system, I already know which features I want to pick. I am picking the, let's say, color of the skin, I am picking the location of the eyes, I am fixed, then I develop my classifier. But sometimes I can say that while I am training my system, I will let my system to choose the features. Usually neural network, for instance, decision tree are in this form. While the classifier is classifying, it also learns which features are good to pick them up. Now, let's talk about the univariant method. Now, in the univariant method, we will look at one variable at a time. Look at these 2 variables. First, let's focus on this one. Here we have 2 variables, x2 and x1. And I need to pick up one of them as a very good variable which can help me to discriminate. Now, it has written that x1 is more significant than x2. Let's look at it. Why x1 is better than x2? Because it helps us to discriminate much better. In other words, as our friend mentioned, it varies a lot. Look, what I do, for my x1, I put the data. How many data do I have? 6. 1, 2, 3, 4, 5, 6. This is my x1. So I am mapping them on x1. Okay? So these are the points on x1. Now, I am rotating this image so I can have the same image for x2. So what happens, I have this. 1, 2, 3, 4, 5, 6. And if I map it on x2, what do I get? Even maybe they are on top of each other, but I prefer not to have them on top of each other. So here are my 6 values. Which one is easier to look or discriminate or to detect? x1. So we look at them separately and we decide that x1 is better because it has significant difference. Now here, if you look at x1 and x2, if you map it on x1 and x2, you can see that more or less they are the same. They are discriminating in the same way. But picking up x1 is the same as you have x2 already in your map. It's look like the line y is equal to x. If you have the line y is equal to x, do you need to need y and x at the same time? No. If you have x, you know you have y. So they are very highly correlated. So if that is highly correlation, then we have to be careful. No correlation correlation between the candidate of the features. Why? Because if you are picking up x1 and x2, you have done something bad. Because if x1 is bad, x2 will be also bad. Or if x1 is good, you are boosting it. We don't want it. If we have x1, that is enough. So we have to be careful about the correlation and about the significant difference. We know that dependency and correlation are related to each other. In dependency, a square is equal to 1 minus correlation square. You should have the formula soon. So, question, how can we have talked about this significant difference? But how can I understand things are different, significantly really different from each other? What did I did in here? I look at the Manhattan distance. I basically look at the differences. So one of these ways, looking at these values, mapping them and look at the distances. But usually, we can have information-based significant difference. In other words, I will look at the entropy, or I'm calculating the gain, and I see that how varying they are. If I have good differences in information, in entropy, then it means that this is good. I can choose that feature because it has differences. I can look at the statistical method. By a statistical method, I am talking about, let's say, t-test. I don't know if you know t-test or not. I will do an example of t-test and you can see how we can use t-test in order to say that which feature is better. Or we can use t-test if we are dealing with a normal distribution and continuous data. And if the data is not normal, we have to look at some other test. But we know that if we have big data, because of central limit theorem, what is the tendency of the distributions? Gaussian or normal distribution. You remember central limit theorem? Based on that one, I will go towards normal. So t-test is very popular in most of the data that you will handle. We will use the t-test. And if we have the categorical data, the data which are represented in different categories, chi-square test is the type of test that people usually use. Now, the second thing apart from the difference was independency. We said that if they are correlated, I don't need to have the value of y and x because they are representing each other. So, how can I calculate the dependency and independency? Independency squared is equal to 1 minus correlation squared. If the variables are very correlated, highly correlated, what is the maximum value of correlation? 1. If they are very correlated, what can I say about the dependency?
0.
What is 0? Independency is 0. So what can I say about the dependency? So they are highly dependent. They are depending on each other. Now, then calculation of correlation is important. Usually we are using the Pearson correlation formula. Do you remember the Pearson correlation formula? Covariance of x and y divided by variance of x multiplied by variance of y. This is how we were calculating the correlation. I don't have it here. Now, in previous slide I said that this test is very important. We want to look at the t-test in order to see which type of features we have to choose. Now, the t-test works in this form. You have to calculate a few variables in order to find out and make a conclusion which feature is good. So between x1 and x2, which one do I have to choose? You will calculate a variable called t. How you calculate it? You have a set of data. So you will have sets of data. You calculate for the value set 1, for x1 you calculate the mean, for x2 you calculate the mean. For x1 you calculate the sigma, for x2 also you calculate the sigma, and you put them into this formula and you calculate the value of t. Similarly, we are calculating a term which is called degree of freedom, df, by using the formula which is given. So after you have calculated these two numbers, we will have a table, the t-test table, which you can look at the values and numbers and calculate some other terms. How we can do it is this. Assume we have this data. Assume we have this data for data x1. If we look at the value of for x1, the mu11 is 2, sigma 11, if you calculate it, is 1. Similarly, mu12 is 1, and sigma 12 is 1, and we are calculating t. How do I calculate t? By this formula, and df by this formula. So you replace them and you calculate it, you find a value for t and df. The question, the scenario, always give you what is the cumulative probability values. It will be provided to us. Why do I need it? I need it because when I look at the table, I have the tier of different cumulative probabilities. The example that I showed you said that choose this cumulative value to be 0.975. Now, I also have calculated the DF. I already have calculated DF, and DF is 4. So I come to the table and I say that for DF4, this is a big table. I have put it in module, you can download it. For T4, with this cumulative probability, the value of T is 2.776. Now, I am calculating and I'm looking at it. T is T4, 0.97 is 2.75, and T is 1.22 after I calculate it. If this value is greater than the value of T that we have calculated, it means that it's not a good feature. We don't want it because it is not discriminative enough. It doesn't make significant difference. Now, I look at x2, and I calculate the same thing, and this time when I look at the table, I find the value is 2.75, whereas the value of t was 3 point something. And because the value of t is greater than the value of the t-test, so I conclude that x2 is a good feature. But before I calculated with the t-test, I could actually look at the data and understand that x2 is better than x1. Why? Look at this and tell me that why do you think I have to have this feeling that x2 is better than x1?
Because in x1 they are x2 are separated better.
Yes, but why? I am sure that you know it. Maybe you cannot put it in the
It
word.
looks like x1 equals to x2, like with this. The function is like that. x1 is equals to x2.
It's the same thing that they showed before, that it varies more, still varies more.
Yes. Tell me something in here, in this specific example, that when we look at it, we have to say that, x1 is very bad. Exactly. If I look at x1, let's map everything on x1. This 2 point is 1 point, this 2 point is 1 point. So if I give you this point, which of these one do I mean? We don't know. So we cannot discriminate. Now when I look at x2, let's map everything on x2. This is here, this is here, this is here. So every point are not overlapping on each other. So it means I can discriminate them. So by looking at this one, it was a very easy case, of course. I could say that x2 is better than x1. So I even don't need to go and calculate the t-test. But if we have more complicated scenario, then we can look which how the t-test is behaving. Of course, you can always look at also the Pearson correlation, and by looking at this correlation, we can come to some conclusion whether we have good features or bad features. Now, there is a term. If the correlation is high, it is good. What is the highest number that we can get in here? 1. When do I have one?
And they are highly correlated.
When do I have Pearson correlation to be 1?
If they are independent.
If they are independent. Why? Because if they are independent, what is the covariance of x and y? It is variance, it's a standard deviation of x multiplied by a standard deviation of y, isn't it? And then they can cancel each other and I can get 1. So Pearson correlation is also a term that we can use. However, we prefer not to select the features as going there and say that you come, you come, you come, and you come. So what we do, we prefer to have something which is called feature extractor, because then no one can tell us you have favored some of the features and you didn't. So we can go to some other location and reduce the dimensionality or define some optimized formula in order to calculate this feature extractor. So as you can see, we continue to our lecture 5 finish by talking in lecture 6, and we start, so we want to talk about this feature extractor. But we start with an example because theoretically I should be supposed to finish on previous lecture 5, and I'm supposed to start by this lecture. And I have to review what we did on previous lecture, so we start with this example. The example is this. I have several feature sets. This feature set, empty feature set A, B, C, A, B, A, C, B, C, A, B, C. And I have classifier M for all of them. And I get this performance. Question. Which feature set do I have to choose? A, B, A, B, C.
AB.
Why A, B, not A, B, C?
Because its features is less.
Yes. Because it has less feature and performance-wise, they are the same. So, this is what we will choose, and the reason is, as I mentioned, we try to reduce the number of features that we have, we try to have very good performance. Remember, when we are saying that we want to reduce the data reduction, it means that we want to reduce the data in a way that the performance is still the same, or reasonably the same. In other words, assume here AD was, let's say, 97 and ABC was 98. Which one would be preferred? It's still A and B, because reasonably they are the same. But if it will become smaller, much smaller, difference become bigger, we don't choose it. Now, we finished with the univariate, and let's talk about this multivariate, how the multivariate method works. When we are dealing with multivariants, we have a complicated system which talks about generation and talks about evaluation. So what is generation and what is evaluation? So we will start to talk about each of them in a few slides, then we will get back to this slide again, so this diagram will make some sense. Generation, in generation we have several methodologies. The first one is called complete or exhaustive. Complete or exhaustive means that I am going and taking all the features that we have. That's why it's called complete. So nothing will drop. But what's the problem with it?
We need to just compare all features.
We have huge data. We have huge number of features.
Takes a lot of time.
It takes huge amount of time. So that's why that it is always out. Another one is heuristic. Heuristic means that we will get some subsets and we will conduct our test through that subset. But what is the problem is we can miss out some important features. So we define some features, we pick up those features and we conduct all our work based on that features. But who says that this feature is the best? So there is a possibility that we actually miss out some of the important features. And the other one is random. So random seems to be more fair because we can randomly pick up. We can randomly pick up those which are performing very well. So the question is, the question is that which randomly picking up version is good. In other words, we have lots of parameters for picking up the features. If we choose correct features, correct parameters for this randomly picking up, randomly sampling features, we usually get good results, meaningful results. Now, for the evaluation is this. Okay, I have decided one of these generation methods, but how good they are, I have to evaluate them. So evaluation can be happened based on different meanings. One of them is distance. What do I mean? How can I look at the distance and say that the feature is good? What was the definition of good feature?
Far better. If it's far, then better.
If between classes is big, it is good. If within classes is small, that is alright. So we can look at the distance in order to pick up our features. Or we can look at the consistency. What is the meaning of consistency? It means that if I pick up some features, I should have different scenarios, different clusters, different places which I want to put the features. The definition of each of these baskets should not overlap with each other. In other words, I cannot have one location which says that let's have green objects inside it, and another basket which also have the feature of green inside it. In other words, if I have green here and I have green here, if an object which is green comes in, we don't know which basket we have to put it. So they are not consistent. So we can find out, we can evaluate by seeing if the features that we have taken out, they are following this consistency or not. And definitely, an information measure or the distances that we define based on this information measure can be very useful in order to conduct evaluation. Of course, there exist other methods like dependency. We already talked that if we have the line y is equal to x, I need to pick up only x or y. I don't need to pick up both of them. Why? Because it's redundant. The whole story is that I don't want to have all of them. I don't want to be complete. So, another one is the wrapper method. Now, the wrapper method is using something which is called CER, the classifier error rate. We will not talk about it much in this course, but I can tell you that this is very cool. And I think the next slide you will see what is the problem with this one, although it is very cool. And the problem is this. I can use different evaluation method. I can use distance, and I can easily generalize if it is good or not. Because I am looking at the principle of classification, which means that within class small, between class big. I can use Euclidean distance. So, time-wise, I can do it instantly almost. I can look at the information, I can calculate the entropy. Again, similar to distance. We know that with Kullback-Leibler divergence, it's information-based, and although it's not distance, but it's inheriting all the information or properties for this implementation. I can look at the dependency. If one variable depends on the other one, I don't need to take it because one of them is enough. I can calculate the other one through that one. And similar thing with the consistency. However, I cannot talk about the accuracy of any of them. I cannot say that using distance is very highly accurate or it's very low accurate. So this is the problem with these ones. You know, almost time-wise very good, we can generalize it, but we cannot talk about them accuracy. But what do I mean by generality? Do you know what does it mean?
This is the thing that if you apply it to another data set, that it will like stay.
If you use different classifier, nothing will be changed. Or if you change your scenario, I mean not scenario, let's say the database is still, it doesn't change. I want to use, let's say, color information of the skin color information to detect faces. It doesn't matter if I'm using face database 1 or face database 2. It doesn't matter which classifier technique I use. But there is this CER, classifier error rate. As the name stands, it depends on the classifier. So for SVM, it works different than for PCA or for some other methods. So I cannot generalize it. In order to come to the conclusion that which method, which feature is good, I need to do lots of processing. So it needs huge amount of time. But one thing is it is very accurate. So we can be sure if we are using it, we are dealing with a very highly accurate system. And we don't need to change our classifier. If you change it, you have to go from the beginning. You have to adjust everything, all the parameters, because we want to minimize this error rate. And then, so it takes a huge amount of time, but again, it will be very highly accurate. So the question is that, what is our purpose? And how much effort do you want us to put on that one? So is it okay if I use simply an equivalent distance in order to say, yes, this is within this cluster or not? In other words, what will happen if I make a mistake? Nothing, that's all right. If 70% it detects it, that's all right. Or do I want to make a mistake? Like that secure root, which we don't want it. So it depends on the system or on the scenario, we have different way of evaluating. So now this makes more sense. How we are creating, how we are taking the features, we evaluate it based on the method. If this is good, here we are. We go for the validation, for the recognition, whatever we want to do. If not, if evaluation says that no, this is not a good feature, we go back and we pick up another one. So this is how multivariate works. Now, the generation and validation, there exists lots of algorithms for generation and validation of this multivariate feature selection. And as you can see, we have, let's say, relief algorithm, we have decision tree, we have the minimum description length method, and like last year, this is your first homework. We have 1, 2, 3, 4, 5 methods. What you have to do, I want all of you to go and investigate about these 5 methods. Read about them. Of course, Wikipedia is always a good friend. But for each of them, you should write 1 paragraph description, but with your own sentences. So I don't mind of you reading the book, Google, using Wikipedia, but I do mind if you copy and paste. You have to write it by your own sentence. This is not an English test. In other words, I don't care if your sentences are very scientific or very nicely written or not. The slide is available in Moodle, and the assignment is not open. I will open it for you. So I want all of you to go and write 1 paragraph for each. I leave it to you to understand what I mean by 1 paragraph. If you think 2 lines is 1 paragraph, I really have nothing to say. And again, if you think that if you make the font 25, it will be very reasonable, then again, I have nothing to say. Use your common sense in order to make 1 paragraph. It's important for you to understand what are each of these algorithms. We don't really need much about the details of them. Maybe you need it for your project. But in this course, we will focus on, as I said, on feature extractors. So feature selectors are not really hot topic for us. That's why that you do it as homework. I will open the assignment today, hopefully, and you will have 1 week to do it. It's pretty simple. Now, when we want to select features, there exist several methodologies. One of these methods is called naive methods. Let's see what the naive methods are. We will have the features and we have the recognition rate. Okay? And we look at these results, what is each feature resulting in. We sort them and we will say that the first 5 features are the good features, or the first 10 features are good features, and we will pick based on that one. Well, what is the problem with that one? We are not necessarily picking up the best features, because we have to do it for one data set, right? Maybe the data set is a biased data set and the features that we are selecting are not necessarily good. It happens quite a lot that people comes out by doing this naive selection. They pick up some features, but when you go for the long run, a more complicated database, you find that actually those features are very big features. Now, another one is SFS, which is sequential forward selection. At the beginning, we have nothing. And one by one, we are testing the features, and those features which are good, like they cause significant difference, we will put them in our basket and we keep them. And if it is not good, we don't pick it up. Again, from the beginning, we start to walk till end and we pick those which are good. And as we have the sequential forward selection, we definitely have the sequential backward selection, which means that I pick all the features, and one by one I try to delete them. So, which one is computational complexity-wise higher? Backward, because you have all the thing. In order to test, you have to test everything to throw one out. Then you have one less, you test everything to throw one out. So computational complexity-wise, SPS is higher, but most of them are actually high. But if you compare between SPS and SFS, SPS has higher computational complexity. Now, we can have generalized SFS. This time, I don't pick up one features. I will actually make subgroups, and I pick subgroups. So each term, I pick, let's say, a pair or a triple of the features, and I see what is the performance. And if it is good, I put all these triple or this subgroup into my basket. Not necessarily they should have the same size, but they should have some meaning when we are grouping them. And as we can guess, generalized sequential backward selection also is something that we have. And here we have all the groups, and in each run we will throw one group away if it is not good. So we said that we have feature selection versus feature extraction. Feature selection is still till now what we have taught, we have them. We have exactly what we can interpret, what has a meaning, and we try to pick them up. We don't want it much. We want something which helps us better, helps us to discriminate better, and is very irrelevant from this independency and correlation stuff. So what we do, we are doing something which is called feature extraction. We will introduce a few well-known and useful feature extraction techniques, and you will see that we will use them also for classification. But I remember last week I mentioned that although we use them for classification, but you have to be careful that feature extractors are not classifiers. Don't use them as a classifier. One of the most famous one that we will use is principal component analysis. We will also talk about linear discrimination analysis. And the whole story is that I am transferring the features that I have to another domain, another vector space, and then I will try to pick those one out, or I try to discriminate in there. If I pick any of these vectors and I look at them, I do not see anything meaningful. It's just some mathematical representation of some numbers. So this is the main difference. In feature extractor, in feature selection, what I have in my hand is actual features. In feature extractor, I am having some transformation of those ones. Now, we will talk about it in next lecture. I mean, these two lectures were very short, that's why I joined them. Do you have any question? So you understand that our focus is on feature extraction. And we have talked through to find out why we want feature extraction. And what is the difference between this feature extraction and the feature selection? In next lecture, when I start to talk about PCA, I will tell you about the mathematics of PCA. So you will see all the mathematical representation of PCA. I can tell you that it's absolutely very easy. However, if you hate math so much, if you hate algebra, like you prefer not to see it and die, I recommend you to go and review eigenvalue representation on eigenvalue of matrices. Eigenvalues. Have a look at that one. If you have a matrix, what is an eigenvalue? How you can calculate eigenvalue? Of course, we always have our computer to calculate it for us, but it's good to revise it. Although, in the class, I will tell you what they are, but I just quickly, with a bullet speed, I will go over it. But I recommend you to go over that one because it's very useful. Do you have any question? If you have no question, this is the end of lecture for today. You can stop the video, but before you